In section 7.6, we need to remember some things that we learned in pre-calculus about the inverse trig functions. The first things we need to remember is the notation for the inverse trig functions, which should be second nature to you at this point. The inverse sign looks like this. Y equals sine inverse of x. Not to be confused with the reciprocal of sine. This is the inverse of sine. The domain, obviously, is the x's you can put in, -1 to 1. And the range is from -2 to 2. So when we get y values out of this, y is going to be from the first quadrant or the fourth quadrant. In this case, so from negative pi over 2 to pi over 2. Now you need to think about inverse cosine. Its domain is the same as inverse sine, obviously, because sine and cosine values only come between -1 and 1. The range is from 0 to pi. So the y values that come out of inverse cosine are going to be in the first quadrant or the second quadrant. For tangent, inverse tangent, the domain is all real numbers, and the range is again quadrant 1 and quadrant 4. It's important also to remember where tangent is 0 and undefined. So if you're going to evaluate a lot of inverse tangents, it's good to go through your unit circle and just write next to each angle what its tangent is going to be. So next, we need to remember these properties, these cancellation properties. So the cancellation properties for sine and inverse sine, it helps to look at these and read them in a certain way. If you read this as the sine of the angle whose sine is x, that's what an inverse trig function says. The angle whose sine is x. Well, the sine of the angle whose sine is x is x. Same thing with cosine. We say the cosine of the angle whose cosine is x is x. Same thing with inverse tangent. We say the tangent of the angle whose tangent is x is x. So an inverse trig function, if you remember from pre-cal, an inverse trig function finds the angle. This regular trig function finds the sine or cosine or tangent, but if you just had the inverse standing alone, it'd be finding the angle. Let's do some examples from pre-cal. The inverse sine of 1/2, the angle whose sine is 1/2 is pi over 6. And if it had been -1/2, we would choose the fourth quadrant angle that's over 6, 11 pi over 6. The cosine of the inverse sine of √3 over 2, so what we're doing is finding the cosine of the angle whose sine is √3 over 2. The angle whose sine is √3 over 2 is pi over 3. The cosine of pi over 3 is 1/2. Final one, we have to remember that sometimes the book and me will write the inverse cosine as arc cosine. So just remember that before we get started on this one. This one says the cosecant of the arc cosine of 3/5. The cosecant of the angle whose cosine is 3/5. For this kind of problem where it's not immediately available in the unit circle, we draw a triangle. This will be our angle right here. And the angle with a cosine of 3/5 has an adjacent side over the hypotenuse equal to 3/5. You should at this point recognize this as a special triangle. If you don't recognize the 3, 4, 5 special triangle, it's okay. Use the Pythagorean theorem and you can find the other side. So let's find the cosecant of this angle. Well, if cosine is adjacent over hypotenuse, cosecant is the reciprocal of sine, so it would be hypotenuse over the opposite. We'll review these a little more with our classwork tomorrow. So now that we've reviewed all of our inverse trig properties and things you can do with inverse trigonometric functions, and again, we'll practice some more of those examples on the practice work for this section. Let's talk about differentiating inverse functions. And before we really just memorize the formulas, let's think about what does it mean to find the derivative of the inverse sine of x. Well, look, it's the derivative of an inverse. Remember Theorem 7 from section 7.1? It's everybody's favorite, the theorem that we thought wouldn't mean anything and wouldn't amount to anything in life. The Theorem 7 is useful here. Inverse sine prime, or the derivative of inverse sine, is just the same as saying the derivative, the prime of f inverse of x. F inverse prime of x. So sine inverse prime is like f inverse prime of x. So if we wanted to evaluate it according to this Theorem 7 right here, then we would take it and say 1 over f prime, which is cosine, because the derivative of sine is cosine, of f inverse of x, sine inverse of x. So f inverse prime of x equals f prime of f inverse of x. If we've got the, let me erase this mark right here so I can use this space. If we've got the derivative of inverse sine in this form, is that useful at all? Let's think. Is it useful at all to have this formula right here? Not really. It's not really that useful of a formula. Because it's hard to put the x into. We're not going to find this formula occurring really often in any of our problems, so that we could use the derivative. So let's see if we can make this look a little more useful. Sine inverse of x prime equals 1 over cosine of sine inverse of x. That's the formula we're looking at from Theorem 7. 1 over the cosine of the angle whose sine is x is what that really says. So if we're going to look for 1 over the cosine of the angle whose sine is x, 1 over the cosine of the angle whose sine is x, we're going to look at a right triangle. Let's make our angle, and let's just make this angle here have a sine of x. Well, sine of the angle, we can call it theta, equals the opposite over the hypotenuse. So the sine of this angle is going to be x over 1. So x is opposite the angle, and 1 is the hypotenuse. Now to find the cosine of that angle whose sine is x, because that's what we need to find to put on the bottom here, cosine of the angle whose sine is x, we just need to use the Pythagorean theorem. X squared plus, what do you want to call that side? We'll call it y. Y squared equals 1. So y squared equals 1 minus x squared, and that y equals the square root of 1 minus x squared. So we can replace this to make it more useful. So yes, we can make it more useful. And let's replace the cosine of the inverse sine of x with 1 over the square root of 1 minus x squared. So sine inverse of x prime, or the derivative of inverse sine of x, equals 1 over 1 minus x squared. From in the same way, you can derive all of the other derivative formulas for all of the other inverse sine functions. Obviously, we won't go through all of that, but that just gives you a good idea of how we get these formulas and make them a little bit more useful. It's using that Theorem 7 from section 7.1. Let's look at all of the formulas. And these are going to need to be copied into your notes. You might pause the video at this moment and copy these the derivatives of inverse trig function formulas into your notes. You can guess which ones are going to be the most useful and come up the most often. Obviously, inverse sine, inverse cosine, inverse tangent are going to come up pretty often. You don't see the secant, cosecant, and cotangent very often because most things can be changed into terms of sine, cosine, or tangent. But so for memorization's sake, you really, well, since they're related, it's easy to kind of memorize them all, but you want to make sure that you have memorized the sine, cosine, and tangent inverse derivative formulas. So again, just derivative formulas. Now, if we're differentiating, we also are going to integrate. Each derivative formula from this previous page has an integral formula. These ones here are the most useful. 1 over 1 minus, or square root of 1 minus x squared dx. 1 over square root of 1 minus x squared dx equals, that integral equals inverse sine of x plus c. And the tangent one is also useful because this is stuff that you come across. You can imagine coming across that in an integration problem. All of the rest of them, again, just reverse the derivative and you have the integral formula. Another useful formula from this section, go ahead again after I talk and pause the video so you can write all these down. Another useful formula from this section is the following formula: 1 over x squared plus a squared, where a is a constant, dx, the integral of that is 1 over a tangent inverse of x over a plus c. And you do come across this one. You will come across it in a practice problem and a homework problem. So that's one that is going to be important to know as well. Just again, these are formulas. Just put them in your notes. We'll use them in class when we do our practice exercises. In this next slide, I'd like to do one example just to show, because I know that last formula looked a little bit tricky. Here's a quick example to show, and here are the problems. The problems in the lower right-hand corner are the problems on page 461 that we will be working on in class on Monday. Again, it may take us Monday and Tuesday, or Monday and Monday night's homework. If we're integrating something like x over x to the fourth plus 9, you can recognize that as a version of the formula we just looked at, right? So take yourself through these steps. If there's a little u du substitution there, we let u equal x squared. Du is 2x dx. 1/2 du then is x dx. So I have 1 over u squared plus 9 du. The only tricky thing is that you have to recognize what's in this little pink cloud thought bubble here, that 1 over u squared plus 3 squared is what that really says. So your a is 3. Look at that formula on the previous slide, and using a equals 3, we integrate and end up with the following answer. We need to multiply the 1/3 by 1/2 to get 1/6, and then put the x squared back in for the u. And copy down this example, copy down the formulas, and we should be all good for class.